Quick question. Have you ever given someone directions and they completely misunderstood you? Turned left when you meant right, sent an email to the wrong John, or took add water to mean ice cold water straight from the tap? That mix up isn't just annoying, it's actually the whole secret behind how computers think and why some instructions work perfectly while others fall apart. In this video, I'm going to teach you computational thinking, the exact same thinking process that programmers use to solve problems, and one you can start using today with or without writing a single line of code. Let's get into it. So, what is computational thinking? At its core, it's about breaking real-world problems into instructions that a computer, or honestly anyone, can follow precisely and in the right order. Here's how we're going to cover it today. We'll start with a fun starter activity, move into a hands-on challenge, look at a quick programming demo, and finish with a few questions to check what's stuck. Let's start with what you should walk away knowing. By the end of this video, you'll understand 6 things: what computational thinking actually is, why it's useful way outside of computing, what decomposition means, what an algorithm is, why sequencing, the order of steps really matters, and finally, how to take a real-world problem and turn it into a clean set of instructions. That's a lot, but it all connects. Let's build it up one piece at a time, starting with an activity that makes this click instantly. Here's a game you can try right now, even by yourself or with friends. The task is simple. Make a cup of tea. One person becomes the computer. Everyone else gives them instructions, one at a time. But here's the twist. The computer has to take everything completely literally. No common sense allowed. No filling in the gaps. Just exactly what's said. Sounds easy, right? It never is. Let's see why. Someone says, put the tea bag in the mug. Simple, specific. That one works fine. Then, add water. The computer adds water straight from the cold tap. Nobody said hot water. Then, boil the kettle. The computer tries to switch it on. Completely empty because nobody said to fill it first. Every single failure here isn't the computer being difficult, it's the instructions being incomplete, and that's exactly the lesson. That tiny tea-making disaster actually reveals 7 huge ideas: ambiguity, precision, sequencing, assumptions, inputs, outputs, and algorithms. Add water was ambiguous. It didn't say hot or cold. We needed more precision, saying exactly what we meant instead of leaving it open to interpretation. We made assumptions the computer didn't share, like assuming everyone knows you fill a kettle before boiling it, and the order, the sequencing of fill before boil mattered more than we realized. And there's also inputs and outputs hiding in here. The instructions we gave were the input, what the computer actually did was the output, and the whole list of steps start to finish, that's an algorithm, which is really just a fancy word for a set of instructions done in order. Every one of those ideas is a building block of computational thinking. Now, let's actually define the thing properly. Here's the definition. Computational thinking is a way of solving problems by breaking them down, spotting patterns, focusing on what actually matters, and writing clear, ordered steps to reach a solution. Notice what's missing from that sentence. The word computer. That's on purpose. This is a mindset, not a piece of software. You don't need a laptop to think computationally. You need clarity. And that's why this skill shows up everywhere: cooking, following or adapting a recipe in order, getting places, planning a route and working around delays, money, budgeting and comparing options, planning events, making everyday decisions, even just working with other people and giving clear instructions. Computational thinking isn't a computer science topic that happens to be useful elsewhere. It's a life skill that computer science happens to formalize. So how do we actually do computational thinking? There are 4 building blocks, and they always happen in this order: decomposition, break the problem into smaller parts; pattern recognition, spot similarities to problems you've already solved; abstraction, Ignore the detail that doesn't matter right now. Algorithm design. Write the ordered steps to the solution. If you're following along in a classroom, a great trick is putting these 4 stages on posters around the room and physically moving between them as you work. Let's break each one down properly, starting with decomposition. Decomposition means breaking a big, complicated problem into smaller, manageable parts, so each part is easy to solve on its own. Take making a pizza. That's actually 4 separate jobs. Make the dough, prepare the sauce, add the toppings, bake it. 4 small solvable tasks instead of one big overwhelming one. That's decomposition in a nutshell. Next, pattern recognition, spotting similarities between this problem and ones you've already solved so you can reuse a solution instead of starting from scratch. Every hot drink, for example, follows the same pattern. Boil water, combine, wait, serve. Once you've solved it for tea, you've basically solved it for coffee or hot chocolate too. Spot the pattern once, and you save yourself from solving the same problem 5 different times. Then there's abstraction, ignoring detail that doesn't matter right now, and focusing only on what's relevant. A bus times app doesn't need to know the engine size of the bus or the driver's name, just the routes and the times. Think of a map of the London Underground. It doesn't show real distances or the curves of the tunnels, just the information you actually need to get from A to B. Stripping away the noise is just as important as breaking the problem down. And that brings us to algorithm design. An algorithm is simply a precise, ordered set of steps that solves a problem or completes a task. Look at our tea example, done properly this time. Fill the kettle, boil it, tea bag in the mug, pour the water, wait and remove the bag, add milk or sugar, serve. 7 clear steps. But here's the part people underestimate. Swap step 1 and step 2. Try to boil an empty kettle, and the whole algorithm breaks. Sequencing isn't a nice to have, it's not optional. So here's a challenge for you to actually practice this. Pick one of these real-world problems: making pasta, planning a holiday, getting to college, buying a car, organizing a birthday party, saving £1,000, or making a pizza. Pause the video and run it through all 4 stages. Decompose it, look for patterns, abstract away the irrelevant detail, and design the algorithm. If you're doing this in a group, physically move between stations for each stage. This is where the theory actually becomes a skill. Now here's something that might surprise you. If you wrote out the tea making steps just now, you've already written an algorithm. And an algorithm is basically one small translation away from being a computer program. Fill kettle, boil, teabag in mug, pour water, wait, serve. That's the same shape as a piece of code. Programming is simply turning an algorithm into instructions a computer can actually understand and execute. Let's see that translation happen. Here's a tiny snippet of real code. Don't worry about memorizing the syntax. Focus on the big idea. Console.WriteLine, open parenthesis, quote, enter your name, colon, quote, close parenthesis, semicolon, string name equals console.readline, parent semicolon, console.WriteLine, open parenthesis, quote, hello, space plus, name, quote, close parenthesis, semicolon. Line 1 is output, an instruction to the user displaying a message on screen. Line 2 is input. It captures whatever the user types and stores it in something called a variable. Think of a variable as a labeled box. We're calling this box name, and whatever the user types gets placed inside it, ready to be used again later in the program. Line 3 is output again, this time combining that stored value into a brand new message. That's it. Input, storage, output. The exact same 3 ideas from our tea example, just written in a language a computer can actually run. Everything we practiced with kettles and tea bags, you've just watched translated line by line into real code. Before we wrap up, test yourself. Pause here if you need to, and answer these 4 questions. What is computational thinking? What is decomposition? Why does sequencing matter? And can you give one example of an algorithm from everyday life? If you can answer all four confidently, you've got it. Let's recap the four building blocks one more time. Decomposition, break it down. Pattern recognition, reuse what works. Abstraction, ignore what doesn't matter. And algorithm design, order the steps precisely. Computational thinking isn't about computers. It's about thinking clearly in order about any problem. And that's a skill that will serve you whether or not you ever write a line of code. If this helped things, click, hit subscribe. Next up, we'll take one of these real-world problems and actually turn it into working code, step by step, live on screen. Drop your chosen challenge problem in the comments. I read everyone, and I might pick yours for the next video. Thanks for watching, and I'll see you in the next one.